In previous videos, I covered the concept of the mole and how a mole is just a large number, an Avogadro's number of some particle. And I also covered the atomic mass unit, which is a very, very small unit of mass that we use to report the mass of an individual atom of an element. In this video, I'm going to expand on those concepts so that we're not talking about the mass, the average mass of a single atom, but now we're going to expand that to talk about the mass of a mole of those atoms. So first of all, the average atomic mass, remember it's an average because there are different isotopes of each atom. So the average atomic mass that is given on our periodic table represents the average mass in AMU, atomic mass units, if we're talking about a single atom. But because of the number that was chosen for Avogadro's number, this mass value that we find on the periodic table is also the number of grams of mass if we have an Avogadro's number of those atoms. So just to recap, this number right here below the symbol, the 12.011 for carbon, that is the mass of a single carbon atom in atomic mass units, and it is also the mass of a mole of carbon atoms, an Avogadro's number of carbon atoms, if we consider the units to be in grams. A simpler way of saying that is a mole of carbon atoms has a mass of 12.011 grams. Okay? So the average atomic mass given on the periodic table represents the average mass in AMU for a single atom, and the mass in grams for a mole of those atoms. So we've got a couple of problems here, and they are conversion problems, and we're going to use the gram masses because we're going to be talking about moles of particles, of atoms. So for example A, what is the mass in grams specifically of 2.40 moles of oxygen atoms? So I'm going to set this up quickly. 2.40 moles of oxygen atoms. And over here on the right, we want the mass in grams of oxygen. Okay? So with that in mind, I'm going to go ahead and let you know that it is a single conversion step. Hopefully, again, this is a review for you. I would like for you to pause the video and complete this problem and get the correct answer with the correct sig figs, and then also go on to example B. Remember now we are using the mass in grams for oxygen atoms. Oxygen atoms, there is just a single oxygen. We're not talking about oxygen gas, the molecule, which has two oxygen atoms in it. So this is not O2. This is just a single oxygen atom. And now we're going to have 2.40 moles of those oxygen atoms. And we want to convert that to grams. So please pause the video, continue this work, and do example problems A and B. And when you're done, resume the video and I will work these problems out for you. Okay, I'm assuming you're coming back from pausing the video. So we already have this first one set up. We want to convert from moles of oxygen to grams of oxygen. So moles of oxygen goes on the bottom and grams of oxygen on the top. And again, notice that it is not O2. That's not oxygen molecules, it's oxygen atoms. Looking at the periodic table, we see that the mass of a mole, another way of saying the molar mass, the mass per mole of these atoms is 15.999 grams per 1 mole. 15.999 grams of oxygen per 1 mole. So now we have our numbers in there. We just need to do the calculation. 2.40 times 15.999 equals. The denominators are all ones, so I don't need to divide by anything. So my answer is 38.3976, and I need to round to 3 sig figs here because that is the number with the fewest number of sig figs in this multiplication problem. So 38.4 grams of oxygen. Okay. And before we move on, we always like to check to see if the answer makes sense. Well, if 1 mole of oxygen weighs about 16 grams and we have 2.5 of them roughly, then it should be about 2.5 times 16. So yes, we are in the right range for that answer. Second problem, how many moles of boron are in 35.0 grams? So we have 35.0 grams of boron. And we're looking for moles of boron. So there's a conversion factor that will let us do this in one step. It goes from grams of boron to moles of boron. The moles is always 1 mole in these conversions because this is the molar mass. The molar mass is the mass per mole, the mass per 1 mole. So it's per 1 mole, the grams per 1 mole. On the periodic table, we see that the mass of a single boron atom is 10.811 AMUs, but the mass per mole of boron atoms is 10.811 grams. So it's that number, 10.811. So we have our numbers. Let's multiply them through. 35.0 times 1 equals. So I get a 35.0 on the top, and then I divide by nothing, 1 over here, and then this number. So basically this problem is 35.0 divided by 10.811. And as you can see, I should get an answer that's somewhere around 3.5. 35 divided by about 11, which is about a little over 3. Rounded to 3 sig figs, 3.24. Moles of boron. So these are basic, very fundamental molar mass calculations, and we can use the molar mass as a conversion factor to convert from moles to grams or from grams to moles. Again, I hope this is a review for you. We're going to continue on and do a little bit more review. So on the next page, a little bit more complicated problem, but not too much more, I hope. So this is another problem that is going to require our molar mass conversion. What is the mass in grams of 1.10 moles of a substance? The difference here is that we're not dealing with just an atom of an element, but we are now dealing with a compound that has more than 1 atom in it. So that's what this note says. Notice that there's more than 1 atom in this molecule. Well, we approach it the same way. We're going to start with 1.10 moles of pH3. And over here on the far right, we need mass in grams, grams of pH3. So there's going to be a conversion factor here. It's going to be a one-step conversion from moles, pH3, to grams of pH3. Molar mass conversion steps are always per 1 mole. But now we have a little bit of a problem because nowhere on the periodic table of the elements am I going to find the molecule pH3. So, as you may recall, the way that we get the molar mass for a compound or a molecule is that we have to add up all of the atomic masses. So we have to do a little side calculation, side math. So in pH3, I've got 1 times phosphorus equals, and that is 1 times, and what is the atomic mass of a phosphorus? It's 30.974 grams. That's grams per mole. And I've got 3 hydrogens, so that's 3 times hydrogen. So that's 3 times, and the atomic mass of hydrogen, 1.0079. So 1.0079. Well, we know that 1 times that is 30.974 from the phosphorus. 3 hydrogens. We do that math and we get 3.0237. And then we have to add these up, right? And you'll notice that in the addition, because this is now an addition problem, my answer cannot be more precise than that column right there. It cannot go out to that column. It can only go out to that column. So I add those two numbers on my calculator and I get 33.9977, and rounded to the third place past the decimal, that's 33.998 grams per mole for pH 3. Okay? So that's a little side math I had to do, a side calculation I had to do in order to get this number. Now that I've got it, I can plug it in right up here, 33.998 grams of pH 3 for every mole of pH 3. Again, hoping this is a review and you remember how to do atomic and molar masses for compounds. Sometimes they require doing a little bit of side calculation to get a number that you can plug into your main dimensional analysis. Now that we have these numbers, I can multiply across on the top and I'll have my answer because all the denominators are ones. So 1.10 times 33.998 equals 37.3978 rounded to 3 sig figs is 37.4 grams. So if you have 1.10 moles of this substance, then it's going to weigh 37.4 grams. Does that make sense? Yes, if 1 mole weighs 33.998 and we have about a little over that, then the answer should be a number just a little bit over that, and it is. Moving on to another example here, and we are continuing on with our molar mass conversions. Example D, what is the mass in grams of so many atoms? Now we're going to have to do a two-step conversion. I cannot go directly from atoms to mass in grams. I'm being asked for the mass in grams. So that's a clue right there that I'm going to need to go through the molar mass conversion step. Since I'm going to go through the molar mass conversion step, which is the one that deals in grams, I'm going to need to convert these number of particles into moles first. So let's start with the number of particles, the number of atoms. 4.05 times 10 to the 24th atoms. And I'm asked for the mass in grams. And this is atoms of iron, right? Atoms of iron and grams of iron. So again, there's no single conversion step that will allow you to go from atoms to grams because atoms are not measured in gram masses. Atoms are measured in AMUs. So to get to grams, we need to get to moles first, and then we can do a mole to gram conversion. So this is going to be a two-step conversion process. So I'll put the placeholders there, and I'll ask you to pause the video and continue to work that problem, get the answer, and then resume the video and I'll show you my work. Okay, assuming you're coming back from pausing the video and doing this problem, let's go ahead and put atoms of iron, and we're going to go moles of iron, right? That cancels the atoms of iron. So you can see that I'm now into moles, and now it's pretty easy to do a molar mass conversion from mole to grams. And this molar mass conversions are always for 1 mole, right? For particles like atoms or molecules or electrons or whatever to moles, that's also always for 1 mole. How many atoms are in a mole? It's an Avogadro's number. So 6.022 times 10 to the 23rd. How many grams are in a mole of iron? This specifically is iron. I should be diligent in putting that in there. Make sure the substance is always listed. The periodic table tells us 55.845 grams of iron for every mole of iron. Now I have the numbers, and you'll see that I have numerators and denominators, and the denominator over here is understood to be a 1. It's understood to be over a 1. So typically what I do to avoid the possibility of making a mistake with a parentheses error in my calculator, I will multiply everything across on the top and hit the equals button to get my answer for all the numerators being multiplied. And then I will divide it by the denominator being only this number in this case. So let me do that. 4.05 EE to the 24th, exponent to the 24th, times 1, I don't need to input, but 55.845 equals. So this is the number that I get from multiplying across my numerators. And now I'm going to divide that by this denominator. The others are 1, so I don't need to deal with them. So divided by 6.022. And on this calculator, I have to hit the EE button to hit the exponent, 23. Just a word of caution. To enter this multiplied by 10 to the 23rd, this times 10 to the 23rd, that multiplication symbol, we do not use the regular multiplication symbol on our calculator for that. We do not use the calculator multiplication symbol. We have to specifically enter it as an exponent. Otherwise, we're going to get the wrong answer. So that times 10 to the 23rd, we don't use the calculator's multiplication button to signify that. Okay? So now I can hit my equals. There's my answer. And how many sig figs do I need? I have 3 here, 4 here, 5 here. So my answer should be in 3 sig figs. So 3.7 and 6, 3.76 grams of iron. We always ask ourselves, does that answer make sense? All right, let's check our answer here and see if it makes sense. And I think you're going to spot something right away. Right up here, we can tell that I had more than a mole of iron atoms, right? Because a mole is times 10 to the 23rd, right? So I've got much more than a mole of atoms of iron. And if each mole weighs 55, almost 56 grams, and I've got more than one of them, then I should have an answer that is significantly more than 55.845 grams, right? That's the mass per 1 mole, and I have well more than a mole, so something has gone kablooey with my answer here. So this is a good opportunity to make sure that we are checking the answer to see if it makes sense. And I don't know if you spotted it. I didn't spot it until I wrote down this answer and then I checked to see if it makes sense. Had I not done that, I would not have realized that I had a calculator error. But obviously this answer is too small to be the correct answer. So I went back and I replugged everything into the calculator and I redid this math. And sure enough, I did get a different answer. I get 3.76 times 10 to the 2. So 376 or 3.76 times 10 to the 2. Either of those is acceptable, the standard notation or the scientific notation. Had I been taking a test and I left my original answer on there, I would have gotten it incorrect. How did I know that it was incorrect? How did I know to go back and fix it? Because I took that step before I moved on of checking. I mean, I've been doing these sorts of calculations since the 80s, right? But every now and then you'll make a mistake in your calculator or you'll read the calculator incorrectly. So you always need to check your answer to see if it makes sense before you move on, and then you might actually spot an error that you've made. So the answer here is 3.76 times 10 to the 2 grams of iron. Does that make sense? Yes, because 376 is significantly larger than 1 mole weighs, and we know that we've got more than 1 mole, so that's good. And that's how we use molar masses for conversions between grams to moles or moles to grams. Sometimes you will need to get into moles in order to be able to use the molar mass conversions.